Okay. Hi, everybody. Hi, William. Okay. Hi, it's okay. Can you hear me?
Yeah, yes, I can hear you.
Okay. Thank you. Hi, everyone, and welcome to Nigeria Residency program. This is our first workshop, and we have on the call here, ETHNigeria, that will be taking us on the overview of Solidity and what it means to build on blockchain. So we are looking forward to learning so much. I am Toluwani Ezebele, the East Nigeria project lead, and we are so excited to learn this evening. So if you are live here with us, I want to see your comments so that we can be sure that we are learning together. So hi, Ekete, are you still with me?
I'm muted. Okay. Can you hear me now?
Okay. Yeah, I can hear you. Nice to meet
Awesome.
you.
Okay. Hi guys.
So,
Welcome to the ETHNigeria Residency. It's great to be here. My name is Etiti Talk. I'm a software engineer, I'm also a blockchain dev. I'm a dev rel with Leaks and also contribute to the Ethereum Nigeria community. Of course, I build and grow developer communities. So it's great to be here, everyone. Yeah, so I think I should probably share my screen. Today, of course, is an overview. We'll just take a look at what Web3 is all about, the blockchain, and of course, Solidity. So I think I'll share my screen now. Which screen am I sharing? Okay, please confirm if you can see my screen. I hope you can all see my screen, yes?
okay.
Okay. Awesome. So, yeah, so before we get started, what is the blockchain? I'm sure so many of us have different answers to that question in our own understanding, but generally, I like to use a simple analogy. Basically, consider the blockchain as a piece of computer, right? It's a hardware, basically, but then is a combination of this hardware. So this hardware is owned by different people, and then different people bring together this hardware and then they turn it into one network. And what this means is that instead of storing information on one particular device or hardware, where like a server, where everybody goes to, basically get data or store data. Now, everybody or anybody in a public blockchain can actually allocate their device and contribute to the network, meaning that every piece of information is stored on all these multiple devices, like they are all the same. So if and then there is a consensus part, but basically a blockchain is basically a combination of hardware devices, and these hardware devices are just computers. They offer their storage, they offer their processing power, they offer a lot of things to secure the network and allow for utilization of course, the network. So the blockchain basically is decentralized, distributed ledger, like most people like to put it, meaning that every piece of information there is documented, and then this piece of information is stored across all these different computers, right? And then all these different computers, which are the nodes, so each computer is referred to as the node. So across all these pieces, all these different nodes, they store the same piece of information, right? So it means that the information is valid because the information you find in maybe device one would be the same you find in device 10,000 or 3,000, irrespective of where the device is, right? You don't really need to know who owns the device. Anybody can contribute their hardware to contribute to any blockchain network. And of course, this is always incentivized, sometimes by the blockchain itself, and then, like we'll see as we look further on. But basically, the blockchain is a combination of different nodes that hold the same piece of information. So the main breakthrough in blockchain came with Bitcoin. Bitcoin was able to achieve decentralization, right? Like the ability of anybody anywhere to join the network and then also ensure that the information or the data within the network is valid. So Bitcoin pioneered that. But then Ethereum went a step further. The idea behind Bitcoin, of course, was to have a freedom from financial in short, to have financial inclusion for everyone. That was the vision of Bitcoin, to basically allow anyone to send and receive assets no matter where they are without a third party, which is mostly government and central banks. And then that was working really fine. But then Ethereum went a step further that, okay, we now have like this combination of computers. They have this mass storage units, and then they have this large computation power. Okay, why don't we have like a virtual machine that could literally anyone could utilize this blockchain or this combination of nodes, and then we create a virtual machine that would allow pieces of software to actually run virtually in virtual machine. Like a virtual machine, more or less, is probably a Linux server at the end of the day, most of the time. But then a combination of all these servers, right, which is all the nodes in the blockchain. The combination of all of them basically allowed Ethereum to be able to build the Ethereum virtual machine. So the Ethereum virtual machine is a runtime that allows for execution of code, mostly Solidity or Viper code. It will be compiled down to bytecode anyway. So Ethereum took it a step forward. Um, Outside financial freedom to ensure that we were able to build applications on the blockchain, right? And of course, these are all decentralized applications, meaning that once you have your application on a blockchain, is decentralized, is not it might be owned by someone, the person that deploys the smart contract, but it's not controlled by anyone, meaning that whatsoever logic you have there, once the condition is met, is going to execute, right? And then that brings us to smart contracts, right? So the Ethereum virtual machine is more or less a runtime environment that allows for execution of bytecodes. These bytecodes come from Solidity language, which we'll see later on, but then these are all referred to smart contracts, right? So, like the term says, is a contract, meaning that if the terms and condition is met, then basically whatsoever logic that is there might will definitely execute. So a typical example is we always send tokens, like you receive tokens, you send tokens. A token is basically a smart contract that holds some certain data and then some certain logic. So if somebody's sending you tokens, for instance, that means it has passed the logic that probably would check does this person have enough of this token to be able to send? Does this person have it to pay for gas fees? The address this person is sending to, is it a valid Ethereum address? All of those stuff. So once it checks all of those stuff, of course, the sender is initializing this, right? Normally, like if we compare this to the traditional banking system, so if I'm sending money from one bank to the other, when I send the money, my bank tells me they have sent the money. They don't show me that they have sent the money, right? And then I have to wait until the other person receives the money, and that's their own bank notifying them that maybe something has come in, right? But within myself that is sending and the person that is receiving, we cannot really check out these transactions ourselves. We only initialize them, and then the bank does the rest for us. So, in the logic of the smart contracts, when I initialize a transaction, there is no bank that is going to wait to check and do all of that. The smart contract is living on the blockchain, meaning that it's not controlled by anybody. And then when I initialize a transaction, for instance, sends a certain amount, it first checks, do I have that my amount to send? Do I have money for gas fee and all of that? So if I check all those boxes, it literally just transfers that amount to that person, right? Because the conditions have been met and I initialized the transaction. I've signed it with my private key, so it's authenticated on the blockchain. And then the receiver does not have to wait for a third party to notify him or her, right? So on the blockchain there, he can also check, because why? The blockchain is a combination of nodes, like we said, and all these nodes hold the same piece of information. And then all you have to do is plug into one node, and then you can read or write to the blockchain. So you have things like RPC URLs that basically allows developers to be able to plug into any node and then read and write to the blockchain. So, of course, we are very, very 100%. Um, I'm looking for the right word, but 100% like assured or guaranteed that whatsoever information we are getting from any node is definitely the same information across all nodes, so we can trust the blockchain. So that's the concept of the blockchain. That's the concept of Ethereum, and then the concept of smart contracts. So smart contracts are basically code, right? So this code can be written in a couple programming languages. For instance, you can write Solidity code, which is native to Ethereum, right? So Solidity was developed for writing smart contracts on Ethereum. And then you also have Viper. Viper is also Ethereum focused, but it's Python related. But if you go to like other blockchains, like for instance, Stacknet, you have a programming language like Cairo, although it's still Ethereum based at the end of the day. And then which other? You can also write smart contracts with Rust, right? Polkadot, Solana, and the rest. And then, of course, but Solidity is very, very popular because Solidity was developed solely for the Ethereum virtual machine. But there are other programming languages that you can actually use to write smart contracts depending on the blockchain. But the core of it is that at the end of the day, the human readable logic we write, in this case, the Solidity code, the Cairo code, the Rust code, these are all human readable, meaning that we can easily read, organize our logic based on the syntax of that programming language, right? And then, but when it comes to the EVM, the code we write in Solidity is compiled. So Solidity has a sock compiler, meaning that it's going to compile into bytecodes. And basically, these bytecodes are going to be the EVM understands these bytecodes. Each of these bytecodes basically literally translate to opcodes. I'm saying too much. I think I need to share a little extra on my screen to explain this. So this is what happened. Ethereum has what they call operation codes. It could be it's represented by two numbers, sometimes 016030. So when you compile your Solidity code, your byte code, every 4 bytes of your byte code translate to an operational code on the EVM. So that is how the EVM is able to understand the logic from your bytecode, right? So this is a little low level, but nothing to worry about. There. So, but just get the understanding that at the end of the day, your Solidity code gets compiled to bytecodes, and then the bytecode is what lives on the Ethereum virtual machine. So when you deploy your smart contract, you are actually deploying bytecodes, and then when you deploy your bytecodes, the Ethereum virtual machine is going to return an address. The address is basically the memory, like where this particular bytecode lives on the blockchain. And then with the address of that smart contract and of course the ABI, the application binary interface, you are able to read and write to the blockchain. That means you are able to plug your application to the blockchain. Yeah. I'll move a step further. Okay, Solidity. Like I said, Solidity was developed solely for Ethereum, of course, and it compiles down to bytecodes, of course. But then, just like every other programming language, Solidity is quite similar to C and JavaScript because it's um, to, kind of like was created from around the concept of C, JavaScript, and a combination of Python. So this means that Solidity is statically typed. What this means is that if you are coming from a different programming language, like say JavaScript, Python, any other programming language, especially Python, guys, right? So we declare variables without declaring the types. Also similar for JavaScript, except if you are like a TypeScript person. Even though Python has typing, but except you're a TypeScript person. So in Solidity, for every variable you declare, you have to declare the type so that the compiler knows at compile time what type you are referring to. Remember, you're building applications that are going to be deployed in a permissionless system. That means that every piece of information has to be defined. Your logic has to be really, really defined, because once you deploy it on the blockchain, it is immutable. You cannot change it, right? Okay, so Solidity is statically typed, meaning that, of course, for every variable. So if you want to declare, say, somebody's name, you have to let the compiler know that you are talking about a string. So you have to declare that variable as a string. We also have integers. Mostly on the blockchain, we use unsigned integers. The reason being that it would not allow for negative numbers, and then you can be sure that you not have, although it's sorted out with Solidity version, I think 0.8.22, but then there used to be the overflow underflow problem. But mostly we use unsigned integers because the blockchain basically would not deal with negative numbers, right? And then Solidity is contract oriented. Look at it as an object oriented programming concept. So yeah, it's object oriented, right? So every smart contract is embodied in a contract object. So you declare it with the contract keyword, the name of the contract, and then the object of your smart contract. The object here being the logic of what you want your smart contract to do. And then, like I said, it was influenced by JavaScript, C++, C, of course, also, and Python. So what this means is that if you are coming from any of these programming languages, you'd be the syntax is quite familiar, right? So it's also Turing complete, and of course, the performance. It means that you can also perform heavy computations, right? So Solidity is the primary language for Ethereum, and of course, it's used on other blockchains like Hyperledger and the rest. So why use excuse me, guys? Why use Solidity? Of course, like I said, Solidity, given that it's influenced by familiar or popular programming languages, it means that developers, it's easy for developers to learn and build with Solidity. And of course, Solidity, since it's native to the Ethereum virtual machine, or it was developed basically for Ethereum, it means that if you're writing or if you're building on Ethereum or any of the layer twos on Ethereum, Solidity will be your go-to language. We also have tools that make things easy. There are tools for actually developing smart contracts, tools like HardHat or Foundry, which of course would also encounter in the course of this residency. All right. So are there any questions? Let me see so far. Time to learn, time to learn. Okay, awesome. Okay, so the syntax, of course, this is like talking about like the data file or the structure of a Solidity file. First and foremost, Solidity has the .sol extension, just like JavaScript has .js, Python has .py, TypeScript has .ts, right? So Solidity has an extension of .sol, and then in the structure of a Solidity file, first and foremost, you have to declare the licensing for your Solidity code. The reason is because you have the legality of is your code open sourced or not. And then remember, you are deploying to a permissionless system. That means that, of course, most of the time your users would want to see or ensure that your smart contract is verified, meaning that they want to see the actual code on the blockchain so that they can trust that whatsoever your smart contract is doing is actually what your smart contract is doing, right? So most time your code will be available to the public. So this also means that people can copy your code, people can copy your code and do stuff with it. So we have the SPDX license identifier for that, where basically there are different licensing. MIT, meaning it's open source. We have an license without the D, not past tense. That means that, okay, it's open source and anybody can use it. And then if you have like a unlicensed with a D, like past tense D at the end of it, it means that yes, it's open source, but nobody should use it. So and all of this is compiled as metadata in your bytecode when you deploy it on the blockchain. So it's always there. So if somebody declared their license as don't use it and then you use it in your application, they can easily go to the blockchain and prove that you actually use what they say you should not use and probably sue you or something. So, but then we have the SPDX license identifier for that. Then we also have next will be the Pragma directive. So Pragma basically tells Pragma is a keyword that activates certain features in the Solidity compiler. So when you do a directive like Pragma Solidity, you're basically telling the compiler that, yeah, because after Pragma, you use the word Solidity, so it's expecting you to declare the Solidity version you want your smart contract to use. There are many versions, like I said. So a word like Pragma would tell the compiler, okay, we want to use this Solidity version. And of course, in all smart contracts, it's always you must always declare this. And if you don't declare it, your compiler would complain because these are some of the metadata that is always added to your smart contract that is deployed on the blockchain. And then state variables, yeah. Like every other programming language, we have variables and we have scope, right? So from you are coming from any other programming language, any variable within a scope, be it a function or just a scope, is local, right? So it's native to that scope, right? So in Solidity is the same. So after having your contract object, and then you declare a variable, any variable you declare outside a function is going to live on the blockchain, right? It's going to be persistent. So those are state variables. So this could be either strings, integers, arrays, or reference data types like mappings and so a state variable, this means that this memory is going to persist on the blockchain and then it's going to live on the blockchain. So a typical example, if you're writing a smart contract or a simple ERC20 smart contract, that's a token smart contract, things like the balance, the name of the token, the total supply, things like that, you would want to leave that as state variables because they would have to live on the blockchain, right? And then maybe within your functions, you can declare any other variable depending on your computation. So we have state variables, we have local variables. So the local variables are within the function. This means that the memory is not persistent. The memory is only utilized within that function call. And after that function call, that memory ceases to exist, right? And then we also have global variables. So global variables basically are blockchain variables, things like block.timestamp, message.sender, that's somebody that is sending the request. So it's stuff like that are global variables. They're available on the blockchain and they are always read only, so you cannot modify them. And then, of course, we have functions. With visibility modifier. So I think when we dive deeper into Solidity, we'll see all of this. So, but the functions here and the visibility means that in Solidity, when you declare functions, or when you declare functions, of course, with the keyword function and then the name of the function, you can basically modify certain things, right? You can modify who can call that function. You can modify who can even see the function, right? So, like for instance, this modifiers here is talking about public, private, internal, external. So, if you modify your function as public or external, or public, anybody can see it, right? Within the function, within the smart, excuse me, within the smart contract, other functions can call that function if it is public. And then, but if it's external within the smart contract, other functions within that smart contract cannot call it, but functions outside the smart contract can call it. If it's internal, right, it means that, of course, functions outside the smart contract cannot call it, but it will be available for functions within the smart contract. And then since Solidity is, of course, object oriented, it means that it supports, of course, inheritance, polymorphism, and all the rest of that comes with object oriented programming. So what this means is that if you have another contract that inherits from a previous contract that has a function that was declared as internal, the function B would definitely see that and can use it. But if you declare it as private, it's only available in function A, and function B will not see it, and the outside will not see. But of course, we'll dive deeper into that. But the concept here is that Solidity functions, you can modify things, you can modify who can call the function, you can modify who can see the function, right? And of course, you can also declare what that function return. That's the return type. Do we also have events in Solidity? So think of event as if you're a backend developer, right? Think of event as logging, like when you are logging your server or console, logging things out, right? So events basically help us to, since we are dealing with a permissionless system, right? That means that there's nobody that is going to be checking or keeping track of things for us, but all of these things are going to be available on the blockchain. We just need to go find it. And then when you have millions of transactions, it becomes a hell of a job looking for certain information, right? So the best way to do that is to have events. So events basically are triggered normally within your function calls at any point you want it to with the emit keyword. And then what it does is that it leaves like a log on the blockchain. So you can go there and then you can see certain information. For instance, if you had going back to our um, sorry, I don't know, somebody's anyway, going back to our token smart contract. So you probably want to have an event that is emitted probably when somebody sorry, excuse me, you probably want to have an event that is emitted when maybe somebody sends a token, right? So you want to be able to keep track of anything, who sent the token, how much did the person send, where did he send it to, right? Basically, so you can do that by emitting an event that will log on the blockchain the address that sent that amount, the address, the amount, and then the address the person is sending to. So event does that. And then, of course, we have modifiers, like I said, functions, just like your state variables, right? And functions. Your state variables also have visibility, meaning that you can declare it as public or you can declare it as private. So you can also do that. Then you also have modifiers. Like I said, modifiers are like custom logics that you declare within your function. So, for instance, if you wanted certain individuals to be able to call a certain function, you probably want to whitelist those addresses and then have a modifier that would ensure that only those addresses can call that function. So you can modify anything. You can modify it such that only you, the owner, can basically call that function. You can modify anything you want, right? So, yeah. So, taking a key look at Solidity features, data types, I think we visited that. So we have bool. Yeah, I didn't mention bool earlier. Yeah. So we have bool, integers. Of course, bool is a true or false value. Integers, of course, we have negative and positive numbers. Unsigned integers, like I said, mostly we use that because we do not want negative numbers on the blockchain. We also have an address type. So the address type basically tells the blockchain that this is a memory on the blockchain. So every address is a memory on the blockchain. So we also have arrays, we have mappings, and we have structs. I think we also looked at functions, we looked at modifiers, we looked at events, and then of course the concept of inheritance that comes from object-oriented programming that allows one contract to inherit all the functions and state variables in another contract. And then, of course, gas optimization. So earlier I was talking about the operation code and then the byte code and all of that stuff. So for every operation code on the EVM, it has a particular gas price attached to it. Let me see if I can get that. This should be evm.codes, right? So let me see if I can get that out. So basically, every operation code costs gas, and then all your, of course, your smart contract logic, depending on your logic, is going to call certain EVM operational codes, and each of these EVM codes costs gas. So a combination of all your computation is going to determine how much every function call is going to cost. So hence, as developers, of course, you need to optimize to be for all your smart contracts to be gas efficient. I don't even, I need to reshare my screen. Can I add screen? Stop sharing. Just a second. I'm just going to share everything at once so that we don't go back and forth. Okay. Let's share. All right. Okay. So you can see my screen now. Yes, I think you should be seeing everything. Yeah. Okay. So this is what I mean. The EVM. If you go here, EVM.codes. So this is what I'm talking about. These are opcodes 00, 01, 02, and the rest. So when you compile your, let me show you what I mean. So if we go to the playground and then we look for a random, they used to have random solidity codes here. Okay, so this is, for instance, a solidity code, right? Which this is what I mean. So this is the license identifier that talks about if this, of course, MIT means anybody can use it. So this is what talks about if you can use somebody's code or not, and all of this is always compiled in the bytecode. This is the pragma identifier where you're just telling the compiler that using the pragma keyword, of course, this is going to like activate a feature in the compiler. But what we're activating here is the Solidity compiler version, and then we're just telling the compiler that we want to use anything greater than or anything above 0.8.3. So you always have to do this so that the compiler knows at compile time what compiler version to use. And of course, these are metadata that is always going to be added to the bytecode that is compiled or is deployed on the blockchain. So this is the object, the contract object, of course, with the contract keyword and the name of the contract. And then we have this is unsigned integer. Of course, this is meaning that Solidity is statically typed. So we declared the type first, telling the compiler that it's an unsigned integer, and then this variable is public, and then the variable name. So this variable is a state variable, meaning that on the blockchain, you would find at the address of this smart contract that holds this bytecode, you will have some operation codes that translate to this state variable, and of course all these functions we'll take a look at that as we go for lower. So these are functions, and then this is a function modifier. He's saying is view because it's only going to read from the blockchain, and then it's public, meaning that anybody and any function within and outside the function or within and outside the smart contract can call this function. But this is what I want us to look at. So this is the contract. And then if we go to the bytecode of this contract, meaning that after we compile it at this compiler version 0.8.3 or above, we would get something. This is looking too small. But it's normally more than this, right? But this will get something that translates to something like this as the bytecode. And then I was saying that for every two of them, like 60, we see 60, we see 42, another 60, another 00. So all of these are operation codes. So if we come to the opcode itself, and then we see 00 means stop, so it stops at some point, and then it doesn't cause any gas, right? So minimum gas is 0, so you see it halts an operation. And I think we saw a 60, so we scroll down to 60. What does it do? So 60 does a push, and then it causes three gas, right? Three way, which is the smallest unit of ether. So it causes that amount of gas, and then it takes and it gives an output value and places 2 byte item on the stack. So you see that for when you compile your Solidity code, every 2 bytes, or rather it's 4 byte that translate to two, right? So for every 4 bytes of um, your bytecode translates to an opcode, which would be represented by any of these numbers. It could mean a lot. So, but every two of those numbers, you can easily come check. Like you see, S load causes 100 gas, and this does what? It loads word from storage. So that means that if you have a string that you want to store on the blockchain, the minimum you are going to pay is about 100 way. That means storing string on the blockchain is very expensive, right? So there are so many of them, you don't really need to concern much with them. What was I talking? So yeah, so those are the opcodes and then the byte codes and all of that. So moving forward, all right. So getting started with Solidity, of course, like every other programming language, you need an environment to be able to get started with Solidity. You could do this using Remix. Remix is, of course, I think Ethereum Foundation also supports the team behind Remix. So Remix is actually a browser IDE. That means it allows you to run and deploy Solidity code all within your browser. So it gives you like an interface to play with, and then it also comes with some dummy its and some dummy accounts that you can use to try out your logic, right? So we also have Truffle, we have Hard Hat, we also have Foundry, right? So Truffle is nice, Hard Hat is nice. Any of these tools you can use the one that you are most conversant with. But when you're doing like big boy stuff, as we'll see later on, you probably want to use a development tool like maybe Hard Hat or Foundry. Personally, I interchange both of them depending on the project. The only advantage is that they do the same thing at the end of the day, which is it allows you to write Solidity code, write test cases for your Solidity code, deploy your Solidity code, and of course, interact with your Solidity code. You can do that with Hard Hat. You can also do that with Foundry. The only difference is that with Hard Hat, you write your code with, of course, the .sol Solidity extension, but you deploy your logic for deployment, and probably scripts is going to be written in JavaScript or TypeScript if you want. So you write your core contract in Solidity, and then you use another language like JavaScript or TypeScript to basically interact or deploy and interact with that smart contract, which works very well. But also we have Foundry. So Foundry basically um, does everything in Solidity. So you write your code in Solidity, you write your test cases in Solidity, and then it has a CLI that basically allows you to deploy, interact with your deploy smart contract all from your terminal. So, but you can also do that with Hard Hat. Like I said, depends on the one you're most comfortable with. Of course, as we go further down, we would also explore some of these tools. So, yeah, this is a typical example of a Solidity contract. Like we see here again, this is the license identifier, of course, up here, our Pragma version. And this is, of course, a simple smart contract that is a simple storage smart contract. Of course, using the contract keyword to declare it. Of course, we have the name of the contract, some state variables. and then a constructor. Of course, just like every other programming language, we all have constructors, right? If you're writing front end, back end, I'm sure if you're a web developer, at some point in your code, you have a constructor. So basically, a constructor is the first piece of code that runs once your software is, of course, executed, right? So your constructor is going to run first, and then every other thing is going to follow up. So mostly constructors are used for initialization or stuff. But then on the blockchain, when just like also, it's not different on the blockchain because here, of course, if you're writing like a Web2 application, you probably are going to deploy it on a server, and then of course once your what do you call it? There's a name I'm looking for. The base file, like your app.ts or something, your base file that basically your server file that basically kickstarts your application, right? So you have that once you deploy that on your, of course, cloud server, the file runs, and then all the logic follows. In on the blockchain is similar. So once you write your Solidity code and then you deploy it on the blockchain, if your constructor accepts certain parameters, you can impute it and deploy. So once you deploy it, it's going to be the first piece of code that is going to run once your code is deployed on the blockchain. And then, of course, you can start interacting with it. So we have constructors for initializations of any kind of logic. Mostly you could initialize the owner of the contract at deployment. You could initialize certain variables, maybe a token name or even another smart contract address, right? So you could initialize any of those stuff. And then this is the structure of this is just, don't worry about it, it's just a structure. We're just looking at the syntax here. So this is a structure of a function, and then of course you see here the function accepts a parameter, and of course even in the parameter we are still telling the compiler that it should expect a string, and then this string is only going to live temporarily. That's why we have memory. So if a string coming from the blockchain is going to be declared with the storage keyword, which we'll take a look at as we proceed. So this is temporary, and then the name of the variable. And here, when you call this function, what this function does, it simply takes that value and sets the storage on the blockchain to that value, right? So, and then you can get that value back, right? So basically, yep. So you can declare, initialize the constructor, set and get functions, and you can do all of this with Remix, or you can also do it with other development tools like Hardhat or Foundry. Okay, I think we've also addressed this key concept in Solidity, the data types, the booleans, of course. The complex types here is just the reference types, so arrays, mapping, structs, and enums. So take these are reference types, meaning that they allow us to allows us to hold together a structure of different variables, right? It could be a structure of anything. For instance, it could, like this example here, it could be a structure of and then we map that to an address. What this means is that every time we pass in that address, we should be able to get at that address all of that information from that struct for that particular address. So this is very, very helpful. Instead of iterating over arrays, right? Because remember, every time your function does a computation, these are opcodes, and then every opcode has a certain minimum gas fee. Depending on the network, you might pay higher, right? So you want to make sure that instead of looping through an array to look for maybe the student objects from the residency, we can easily map a student's address to their struct. So when we input the student's address, we get the information on the struct. So that's what mapping does. Mapping is more of a key value pair. So you map a value to a key. It could be anything. You could map a string to an assigned integer. You could even have a mapping of a mapping. So take a look at all of that. Of course, enums allow us to define certain states. Like for instance, if we're still using the concept of our residency example, so in the student struct, maybe one of the information there would be maybe the status of their program, which could be ongoing or maybe completed, right? So a struct would allow us to define that state. And of course, we can always reference a struct in Solidity by indexing, right? Yeah. So functions, we also did take a look at them. So pure functions, view functions. Pure means that, of course, we are not reading from the blockchain. When you declare a function as pure, it means that you are just doing a computation that would maybe like a utility function that would help other functions achieve certain things. So a pure function does not read or write to the blockchain. You just have to declare it as pure at core so that the compiler at compile time knows how to treat that. If you do not declare it as pure, of course your code will still compile, but the compiler will throw like a warning telling you that you should declare that as a pure function. So then a view function is a function that reads from the blockchain but does not write to the blockchain. So if you are getting like, for instance, when using Steelback, our residency mapping, the mapping of the address to the struct. So if we wanted to like have a function that returns maybe the student details, and then we want to be passing in the student address and then reading from the mapping. So the mapping will return that concept for us. So we want to declare that function as view because we are actually going to interact with the blockchain, but we are only going to read from the blockchain, right? So, and then of course we have yeah, pure and view. So if a function is not pure and then it's not view, of course, you can change the state of the blockchain, meaning that you can have any function that would basically do any modification, send tokens, mark attendance, anything, right? And then it will change a particular state from, for instance, our enum could be changed from ongoing to completed, right? So that is a change of state. So any function that changes the state of the blockchain, if you declare it as pure or view, it will not compile because the compiler knows that your function is going to change the state of the blockchain. And then we talked about this visibility, I think, earlier on, which is cool. The public, the private, internal, and external, right? So, yeah. Modifiers, of course, also modifiers allow for access control, like I said, so you could determine who can see your function or who can call your function. So, and then of course, all of these are access control. So, for instance, in our ETHNigeria residency example, probably if we have like this kind of smart contract, we want to put a modifier that would ensure that only students that registered for the residency or that were admitted into the residency can call that function. So how we can do that? We can do that in two ways. We could have an array of the addresses of this student, and then we can look through them every time a new address tries to interact with the smart contract, which will cost more gas for whosoever is calling that function. Because remember, at the end of the day, the person calling that function is the one that is going to pay the gas. So it's going to be heavy for your users to use your application. So compared to somebody that have optimized, probably would want to have a mapping and then you could have like a mapping of that address to like a boolean value, say true or false. You could have a mapping to bool, say is student, right? So the variable name will be is student, and then when we pass in an address, it's going to return a true or false value. So that way, it's not really looping, but we are achieving the same result, and it's causing less gas, right? So modifiers are for access control. And then we talked about events, which is just to register a certain log on the blockchain at a particular timestamp that certain this and this really happened, right? Okay, and a typical example of the usefulness of events is if you go to like a blockchain explorer and then you are able to see all those information. Those information are only possible because of events, and then of course I know there are indexers that really deep dive into that, but they are really possible because of events. If the smart contract did not emit an event, there is no way anybody would know that funds were sent on the blockchain. You probably have some transactions, but then you will not have any event to tell you what really happened down there. Of course, yeah, you can also send it. Yeah, so yeah, you are. This is a mapping. So this is probably a mapping that is increasing the balance of the color of this byte token function. So byte token would increase the balance of this is going to probably be like a mapping of um, address to unsigned integer balance. Yeah, exactly. So you can actually do this. And then inheritance and libraries. Yes, so I talked about inheritance a while ago. Inheritance allows for, of course, the ability to reuse certain logic without writing it in your own smart contract. So if I know that this smart contract already has this function that does this and has certain state variables that probably I don't want to change, instead of writing or copying that smart contract verbatim, all the functions, all the state variables, I can simply inherit from that function or inherit rather from that smart contract. And then, of course, all the state variables and all the functions in that smart contract would be available in my smart contract, even though I did not write it. And of course, you can do this two ways. Either you have access to the source code of the smart contract you are inheriting from, or you can also in your smart contract, right? So, and then of course, this would be you reading directly the byte code from the blockchain, but you would need to have prior knowledge of the functions in the smart contract anyway. So, inheritance basically allows one contract to inherit the state variables and the functions of another contract. And of course, in the new smart contract, you can add more functions to it, or you can use it like that. Then libraries. Libraries are also deployable on the blockchain, but unlike smart contracts, libraries do not have state variables. They are stateless, basically. They are meant for utility. So you declare libraries with the library keyword, and then of course it could hold certain logic like string manipulations, integer manipulations, or any kind of computation that you do not want to put in your smart contract, right? Because remember, if you put in your smart contract, it's going to make execution more expensive for your users. So what you can do is you can put it in a library, and then you can utilize you can make actually carry out the computation in the library, and then have that result in your smart contract. You can also like import this library into your smart contract, or if it's a deployed library, of course, you need to pass in, like I said, the address and then be able to initialize that address in your smart contract, and then you'll be able to utilize that. I don't know what I'm missing. Okay, so building on the blockchain. All right, so any application that is deployed on the blockchain is referred to as a decentralized application, right? And of course, this means that this application has a front end, just like every other Web2 application. It has some logic, sometimes a back end, but then it's integrated into the blockchain, meaning that a particular logic is utilizing the blockchain for that. So this could be anything. You could completely deploy your full application on the blockchain, even your front end now with Flick, you can do that, or you can deploy a certain logic in your application on the blockchain and interact with it with your normal Web2 application. So of course, but the core is that any application that is deployed on the blockchain is referred to as a decentralized application. And then why this is different with regular application is that two things. First and foremost, is deployed in a decentralized network, not a centralized network. So it means that you have ownership, complete ownership, especially the address that deployed that smart contract. If you initialize the owner as yourself, you have complete ownership of that smart contract, which is fine. This means that no third party can bring down your application at any time for any reason. The application is always going to live on the blockchain, and nobody can control that application, even yourself, except you have certain custom logic pre-deployment, right? So that is one advantage, right? And then also another advantage is that when you deploy on the blockchain, all your application, or I say all your application, when you deploy your applications, of course, on the blockchain, it allows for um, transparency, right? So people can trust your project, people can trust your application because it is transparent. It is doing what it says it does, right? So you won't have people coming or contacting your customer care because a certain blockchain interaction did not go through, or there have been some delays or all of that. You won't have that on the blockchain because all information on the blockchain are transparent, and then once something is done, there is no waiting for anything. There's no third party to wait for. It's either the person has done it or the person has not done it, right? So there's no third party to wait for. So, of course, we use libraries in interacting with our deploy smart contract. Libraries like ETHNigeria, VM right now. You can use that, and then with your deployed smart contract address, remember when you deploy your bytecode, because when you compile your smart contract, your compiler compiles that to bytecode. So when you deploy that bytecode, it returns an address. So that address is the memory to where the bytecode lives, where you can actually interact with that smart contract. And then but you need libraries, right? So you need that address, and then you also need the application binary interface, which is available when you compile your smart contract. So it returns your compiler returns two objects. It returns the bytecode and the ABI, and then the combination of the ABI and the address of the deployed smart contract would allow you to interact with to have a fully functional decentralized application, meaning you are able to interact with the blockchain. And then the other thing, which is the bytecode that the compiler gives, is what lives on the blockchain. So that's how the blockchain knows how to make certain function calls or interact with your or do anything with your logic, right? Of course, developers can call functions, they can read data, they can send transactions, they can do anything. So the blockchain or Web3 basically is about the new internet that is decentralized. So the blockchain is the technology behind that. So this means that apart from sending transactions, which is of course sending funds to people, you can do a lot more on the blockchain. You can build and deploy applications on the blockchain. Now there are even advanced applications, AI based stuff. So you can do so much more on the blockchain because, of course, the blockchain allows for this. The EVM, which is the virtual machine, allows us to run. It gives a runtime environment for executing code. Okay, so I'm also going to look at certain security considerations. Of course, every system has disadvantages, of course. And then with the blockchain, the major disadvantage and advantage at the same time is that the blockchain is permissionless, right? So this means that there is no gatekeeper. You are literally in charge of everything. You're in charge of your security. And then as a developer, when you write your logic, especially logic that has to do with financial assets, digital assets that are worth some financial values, you would always, since it's permissionless, it means that anybody can interact with it, right? Anybody except you custom that logic. So this also means that there will be bad actors that will also, since they can interact with a smart contract, there is no in the case of the Web2 world, if you're going through Amazon, you have Amazon firewall, Google firewall. There is nobody setting up any firewall for you, right? For your deployed smart contract. So anybody can interact with it. So this allows for certain people with the right knowledge to be able to try to either steal funds from your smart contract or just make your smart contract pretty much not usable. Yes, it's very possible. They put your smart contract in a state of constant loop. No other person will be able to use it, and their own function call will not execute. So your smart contract stays in a state of constant loop, meaning that it's pretty much useless at that point. So there are certain security considerations. Reentrancy is the ability to there are certain conditions with the EVM. For instance, when a smart contract receives it, certain things happen. So if there's like a fallback function, when a smart contract receives it, it is automatically going to trigger that fallback function. So with this knowledge, bad actors can use that to, for instance, if your smart contract is sending out money, right? So they can use that to basically, once they receive, they would use a smart contract to receive the money from the smart contract, and then it will trigger the fallback in their smart contract, which will call back into that function. So depending on your logic, of course, there are reentrancy guards and all of that. But if you did not put that, they can customize the logic that would, since it's a fallback, so it means that it's always going to execute until it executes everything in that fallback, or maybe unless a condition in the fallback is not meant. So but if normally in a general case that you did not protect it, it will keep calling back. For instance, if it was calling your withdraw function and then it's withdrawing money. Since it's a fallback function, your smart contract sends it to it, so it's going to trigger its fallback function, and then it's going to call back into your own smart contract, which is the withdraw function that will still send the attacker smart contract more hits, and then it triggers the fallback function again, right? So it's going to do that until there is no more hits to send, and then that function call will fail. In reality, all of this would happen in seconds or less than milliseconds, so you won't even have the time to react. So um, we have all of this, of course, and there are, of course, many, many more we'll take a look at as we dive deeper in the residency. Of course, we also have best practices. Personally, I like to tell developers to keep their code simple. Don't try too much logic, too much complex logic. Sometimes you don't really need to implement the complex technology. You can actually do it simpler. Simple is better. If you check um, all the big players in Web3, like big players like Uniswap, Aave, and the rest, if you go through their smart contracts, they try to keep it as simple as possible because simple is best. It can be when once it's too simple, right? It's it will not allow room for loopholes because of course they had auditors audit this and that, but keeping it simple means that if you can easily identify a problem and you can easily fix it right before you deploy on the mainnet. But once you want to deploy and then you're trying to use the latest technology, the latest concept, the latest EIPs, which is nice, but before you use it, please make sure you really know what you're doing. Okay, and then we have blockchain standard. These are more like Ethereum standards. So we have standards for certain things, standards for why standard is because this standard has been audited that they are safe. and then they are hack proof, meaning that it's unhackable. Um, there's no way to break that logic. Let me put it that way. So it becomes a standard because many people have tested it, many people have tried to hack it, and nobody has succeeded so far. So it becomes like a standard. So we have standards for creating tokens, standard for doing many things, standards for creating wallets, right? So there are many standards to that. We'll take a look at. And then testing and deployment. Of course, like I said, you need test when you're building on Ethereum. Of course, we have the mainnet and then we have the testnet. So just like the mainnet, the testnet is like a replica of the mainnet. So whatever you're doing on the testnet, it's definitely going to be the same on the mainnet. And then just like the mainnet, you need some ETH to be able to pay for gas. That's if you're building on Ethereum, right? No matter the blockchain, you definitely need for a particular token to pay for gas. For instance, if you're building on Solana, you definitely pay gas in Sol. And then if you're building on Ethereum, you pay gas in it. But with layer twos and advancements now, there's a lot of account abstraction going on. So for so many protocols, especially on layer twos, you can literally pay gas fee with any token that you have. So of course, this is good, and then hopefully would come to a time where we wouldn't have to bother about getting it. You can literally across all chains, any token that is available for you or to you, you should be able to use that to pay gas fee. In my opinion, right? But hopefully we would get there. So, guys, I think that has been a very quick overview. We've been able to look at the concept of solidity, and then there is more to come as we proceed in the residency. Thank you very much. I will make this link available so everyone can also have access to it. Yeah. Tolu, thank you very much. Over to you.
Yeah, thank you so much, Officer. It's been a wonderful night learning about solidity and being introduced to what it is. And all, I believe everybody has learned one or two things. So if you have been on this, if you've been with us from the beginning or you've learned something, let's just do something in the comment section. This will serve as so that we can know that we are engaging real people here. And while doing that, make sure that you also the like, subscribe, and yeah, so that you can come back and go through this because definitely you need to come back to learn this. So thank you so much, Etete, for this section. Is there any questions from anybody? You can just drop back to the comments so that our speaker can take it up. Is there any question from anyone? Okay. Okay. So I think if there's no question here on live, question can actually be dropped in the community where the speaker can take it up from there. So thank you so much, Etete. It's been a wonderful section with you, and we've learned so much about Solidity. Even though I'm not a developer, but I think by now I should start calling myself a Web3 developer by this. So awesome, and thank you so much for coming. And yeah, so I don't know, maybe there's anything from Mr. Enoch before you close the session.
Yeah, thank you so much, guys. It's been a very educative moment. Thanks, Etete, for doing justice as usual. Guys, we're just getting started. So, I just want to give you an insight of what's happening. We're going to expect facilitators from Celo ecosystem, Polygon ecosystem. We're trying to get the guys from. Yeah, we already have the Lakes ambassador here. Etete is already here, so we need to get him on his team again, and they just have to like sponsor some segment actually or some bounties. I know the hackers are quite getting ready for what's at stake, and I think we're having a very good time here. Thanks to our project lead at T. for doing a whole lot behind the back. And let me know. I can see you guys. Cool, I can see you guys. Yeah, let's just keep engaging on the chat group, the WhatsApp, Telegram. Um, what you've learned, just try to like articulate it, put it in write up, try to like come up with a technical write up on this. It's kind of like help you keeping abreast. Um, so we'll meet in less than an hour for 6 p.m. Akindele will be on here. So from here, thanks. See, over to you.